Welcome back to The Explainer. Today we're diving into a seriously mind-bending intersection of theoretical physics and the philosophy of science. We're going to push the boundaries of what we actually call reality and ask if everything we know and see is just a tiny, microscopic fraction of a much grander structure. I am incredibly excited to guide you through this.
So are we just a lucky roll of the cosmic dice, or is our universe one of many? This isn't just science fiction, it's the ultimate cosmic detective story. And to solve it, we really need to look at the very rules that govern our existence and ask why they are so perfectly tuned to allow us to be here asking the question in the first place.
Okay, let's dive into this. Here's our roadmap for today. First, the fine-tuning mystery. Then, varying constants of nature. Third, the multiverse hypothesis. Fourth, we'll ask, is this real science? And finally, testing the unobservable.
All right, Section 1, the fine-tuning mystery, a cosmic detective story.
To start, we have to look at the absolute foundation of our reality. Think of the Bronstein-Zelmanov-Okun cube, which basically maps the core of our physical theories using three fundamental constants. You've got G for the gravitational constant, obviously dictating gravity. You've got C for the speed of light, which connects space and time. And H, the Planck constant, ruling the quantum world. Honestly, think of these like the ultimate cosmic dials. If you were to walk up and turn them even slightly, the universe as we know it would change entirely.
And that brings us to a central mystery captured by the anthropic principle. Simply put, this is the observation that the universe's physical and cosmological quantities are incredibly restricted by the requirement that carbon-based life can evolve. Like, why does our universe seem practically custom-built for observers like us? I mean, out of all the theoretically possible settings for those cosmic dials we just talked about, we somehow ended up with the exact combination required for galaxies, stars, planets, and, well, humans to actually exist.
When you map out where carbon-based life is actually possible based on the value of the electromagnetic force versus the strong nuclear force, you end up with this terrifyingly narrow danger zone. Or honestly, it's more like a safe zone right on a razor's edge. If the strong nuclear force were tweaked even a fraction, hydrogen just couldn't form. Carbon and heavier elements simply would not exist. So the carbon currently sitting in your body right now, completely impossible. We are literally sitting perfectly balanced on a cosmic razor's edge.
Moving on to Section 2, varying constants of nature. Could they be shifting across time?
So, it turns out physicists are actively looking for evidence that these constants might actually vary. They're exploring whether these cosmic dials might turn over time. Things like the gravitational constant, the fine structure constant, which we call alpha, and the speed of light. And to test this, scientists are looking at clues from extreme distances and times. We're talking about studying the absorption lines of ancient quasar light from literally billions of light years away. They even analyze a 2-billion-year-old natural nuclear reactor in Oklo, Gabon. What they're doing is hunting for tiny, microscopic fingerprints showing that the laws of physics might have actually been slightly different in the ancient past.
And just to emphasize the stakes here for our very existence, if that alpha dial, the fine structure constant, turns even a bit, ionic bonds fail. Water totally loses its unique properties, like shrinking between 0 and 4 degrees Celsius, which is literally the only reason fish can survive winter. If this dial shifts, stars cannot shine. Period. Any variation completely destroys the delicate equilibrium that keeps our biological chemistry intact. The fact that it hasn't varied wildly is pretty much the only reason we're here to talk about it today.
All right, Section 3, the multiverse hypothesis. Is our universe just one of an infinite set?
So, the primary suspect to solve this fine-tuning problem is the idea that our perfectly tuned universe might just be one of an infinite set. The cosmologist Max Tegmark categorized the sheer, crazy scale of this idea into 4 distinct levels of the multiverse, just to help organize all this mind-blowing physics into an accessible list. Level 1 is just beyond our cosmic horizon. Same physics, but totally different initial conditions. Level 2 represents inflationary bubbles, where entirely different physical constants exist. Level 3 is the quantum many-worlds interpretation, where every quantum event branches into a new reality. And level 4? That is the ultimate ensemble, where completely different mathematical structures are realized as physical realities.
To truly grasp the sheer scale we are talking about, just consider this number, 10 to the 500th power. In the superstring theory landscape, physicists calculate there could be 10 to the 500th power different vacua, essentially different universes, each with its own set of laws and constants. To put that into perspective for you, that completely dwarfs the number of atoms in our entire observable universe. It's staggering. Our universe, with its perfect tuning for life, is just one single grain of sand on an unfathomably massive cosmic beach.
Which brings us to Section 4. Is this real science? The falsifiability debate.
Now, we hit a massive roadblock in our detective story, and it brings us to a major debate in the philosophy of science. Let's talk about falsifiability. This is Karl Popper's famous theory that a scientific hypothesis must make quantitative predictions that an experiment could potentially prove wrong. Skeptics claim that an unobservable multiverse totally breaks this most fundamental rule of the scientific method. Think about it. If we can never travel to or see a level 2 or level 3 multiverse, how could we ever prove the theory wrong? If it can't be tested directly, the skeptics argue, well, it just isn't real science. It's science fiction disguised as math.
But modern theoretical physicists use a slightly different tool here. Enter Bayesian inference. This is a statistical method that updates the probability for a hypothesis as more evidence or information becomes available. We use this all the time to build confidence in theories without requiring direct observation. As we gather more and more data about how our own universe works, like how inflation happened or how quantum mechanics scales, we can mathematically update the probability that a multiverse model is the best explanation for what we see locally.
So you can see the tension here between two very different philosophical approaches. On one side, we have strict demarcation, championed by Karl Popper, demanding direct experimental falsifiability. On the other side, we have what physicist Sean Carroll calls normal science, where evaluation uses abduction and Bayesian inference to simply find the best possible explanation for our data. It's a clash between rigid experimental rules and the messy reality of modern theoretical cosmology.
So the crucial point is captured perfectly by Sean Carroll. He says multiverse theories are utterly conventionally scientific, even if evaluating them can be difficult in practice. Basically, Carroll argues that there is no scientifically respectable way to do cosmology without taking into account what might exist outside our observable horizon. Just because it's insanely difficult to evaluate doesn't mean we should throw it out. It's an ordinary scientific hypothesis, just trying to find the best model for our data.
Finally, Section 5. Testing the unobservable. Hunting for clues.
Here's the final breakthrough. While we obviously can't travel to another universe, we might actually be able to see its shadow. Physicist Mariusz Dąbrowski highlights specific, real-world clues we can hunt for right now in the cosmic microwave background, the afterglow of the Big Bang. We're actively looking for things like extra dipoles causing a dark matter flow, or a weakened power spectrum of density perturbations on large scales, or even imprints of a strange entanglement temperature. All of these would be concrete signs that inter-universal quantum entanglement is bleeding right into our observable universe. And this leads to a super fascinating concept called third quantization. It suggests that universes might actually be created in entangled pairs, exactly like subatomic particles are. Meaning, our universe could still be quantum mechanically entangled with a causally disconnected anti-universe right now. Even though we could never, ever reach it, that entanglement will leave a permanent fingerprint on the cosmos, an extra term in our fundamental cosmological equations that we could actually go out and measure.
Now, I want to push the boundaries of human imagination one last time today. Because beyond Tegmark's 4 levels, we have Michael Heller's proposed Level V multiverse. This suggests the existence of realities governed by completely different logic, not just different math. We're talking about a realm where our very concepts of reasoning, cause and effect, or even truth itself simply do not apply. We couldn't even test this if we wanted to, because our human brains literally aren't equipped to understand the logic it runs on. Which brings us to one final, truly provocative thought. The final anthropic principle suggests that once intelligent, information-processing life comes into existence in the universe, it will never die out. So, if we look out at the incredibly fine-tuned stars, are we merely observing a single, unimaginably lucky universe? Or, through us, is the infinite multiverse finally waking up to observe itself? Thank you so much for exploring the cosmos with me today on The Explainer. Keep looking up and keep questioning reality.